Hi folks, welcome to lesson 4. So finally, after this detour of looking at the idea of limits in general and seeing how the notation and language of limits could be used to describe end behavior and used to describe behavior near vertical asymptotes, we're finally going to get back to that big ticket item. We're going to get back now to rate of change, which is going to be our focus in this part of the course. Okay. And one of the things that came out of uh, our rate of change unit in advanced functions was that, as I say here, we made this really big leap when we realized that we could determine the exact rate of change by using a limiting process. So at the time, we didn't use the language of limits, but now we see that this expression, which represents the slope of the secants, starting at a and ending at a plus h, okay, that if we take the limit as h approaches 0, it's going to give us the exact slope of the tangent. Okay, there's a bit of an issue here because this means that any time, so let's say I've got some function x squared plus 7 and I want to determine the rate of change at x equals 2, I have to go through this process. If I want to determine the rate of change at x equals 2.5, I have to redo the whole process. In fact, if I have to determine the rate of change at multiple points, each time I have to go through this process. And that is not the ideal. So our goal now is to see if there's a way to avoid having to go through that process every time. So I want you to do this example here. So here we're going to choose f at x being equal to x squared minus 2x. We're going to determine the rate of change at x equals 3 using our limit definition. And what I want you to do in doing this problem is see if you can come up with a way to avoid having to repeat this process every single time. Okay, so we're going to pause the video for 5 minutes for you to work on this, and then we'll come back to it. Okay, folks, we're back. So I'm just going to solve this problem, all right, and see if in solving the problem, I can figure out a way to avoid having to do all this manipulation each time. Okay, so here if I'm looking for the slope of the tangent at x equals 3, I'm going to be taking the limit as h approaches 0 of f at 3 plus h minus f at 3 all over h. And of course, the first step is to just input these two things into my function. So I'm inputting 3 plus h into this function here. So 3 plus h squared minus 2 times 3 plus h. And then I'm subtracting that by f at 3, which is just going to be 3 squared minus 2 times 3, 6, which is just going to be 9 minus 6, and of course all over h. Okay? And remember, at this point, I can't just stick h into this expression. Okay? There's something that's giving us difficulty, this h in the denominator. So we know this expression doesn't exist at h equals 0, but there might still be a limit. Okay, so the next step is to do some algebra. So the next step, of course, is to multiply all this out. So what do we have? We have 9 plus 6h plus h squared minus 6 minus 2h. And this here we said was 9 minus 6 is 3. So minus 3 all over h. Okay. And this is where, before I continue on, this is where I want to start thinking about how I might avoid doing this every single time. I would be performing these exact same steps, whether x was equal to 3 or 2 or 1 or 17 or negative 57. The exact same steps would have to occur. Okay, so I'm just going to leave it there for now. Let's keep going. Okay. Now, of course, in the end, what we need to happen is to end up with a factor of h. And here I notice I have 9 minus 6 minus 3. So all the constants reduce out, cancel out. And so here, what are we left with? We're left with 6h minus 2h. So 4h plus h squared. And this is now starting to look very Very promising because I can factor out the h in the numerator, and I've accomplished what I was hoping to accomplish, which was to be left with an expression for which I can determine the limit easily. And as h approaches 0, 4 plus h is just going to approach 4. Okay? So again, all these steps would have been the exact same whether I had x being equal to 3 at the specific value or being equal to any other value. And so this is what gives us the idea to say, well, when we're finding the slope of the tangent, can we just leave that x value as a variable and see if we can solve? Okay, but that means x is likely still going to be in our expression. But what does that mean? It means for any value of x that I choose, okay, this should be producing some new number. Could I possibly end up with a formula that, given a specific x value, would produce the slope of the tangent there? So what I want you to do now is take 2-3 minutes to think about what we've just created. Okay? I'm asking here, what type of mathematical object is this expression when instead of inputting a specific x value like we were doing before, if we leave that as a variable? Okay, so I want you to take 3 minutes, 4 minutes max to talk to your neighbors and see if we can pinpoint what type of object I've just created here. Okay, please pause the video. All right, we're back. So let's see what we've got here. So I've got this expression, limit as h approaches 0 of f at x plus h minus f at x all over h. And the question was, what type of mathematical object is this? So I know that if I choose some specific x value, say x equals 2, okay, what is this going to give me? This expression, let me call it star, okay, is going to produce some number because that's what a limit produces, a number, okay? If I choose x equals 3, this is going to produce some other number. And if I choose x equals 4, this is going to produce some other number. In other words, for each choice of x, this expression outputs some number. And this is where I did not use that word by accident. Okay? What kind of object takes an input, which is a number, and then produces a unique output, which is a number? Because when I stick in x equals 2 here, it's going to produce one single number. So essentially, this represents a function, but a very special function, because what are the outputs of this function? The output is the rate of change of the function at x equals 2, or the rate of change of the function at x equals 3. And this function is what we call the derivative. And I'm sure that is something that you have heard many times in referencing calculus, and this is going to be one of our notations for the derivative, is the function that takes an x value and outputs the rate of change of the function at that x value. Okay? But what we'd like to do is to be able to find a formula for the derivative or the rate of change of a function so that I don't have to go through this process every time I need a new rate of change at a different point. Okay, so this is our goal for this lesson is, can we start doing that? Okay. And what we're going to do is we're going to choose functions at the start where we already know what the answer is. All right. So let's think of the function y equals x. Okay. We know what the rate of change is at every point because I know that it's a linear function and the rate of change is given by the slope and the slope is constant. So I know that whatever function I come up with should just be the function y equals 1. Okay, let's take a look at this this one here. Okay, well, f at x is equal to 5. That's just a horizontal line. So what should the function that gives me the rate of change be? Well, it should just be 0 because the rate of change is always 0. And similarly here, what should the answer give me? Okay, so we're going to do one example together, and then I'm going to ask you to do further ones, the future ones, and we're going to take them up at intervals. Okay, so let's see what we've got here. So what I'm looking for is this expression here, which now I've told you is that thing we call the derivative. So let's put this down. Limit as h approaches 0 of f at x plus h. Notice here we're not picking a specific value. All right, and let's see what we've got. What's that going to be equal to? Well, if I input this into the function x, well, it's just going to give me x plus h. Okay, input x into my function, it's just going to be 8x, all over h. And let's see what happens. Does it give us what we expect it to give us? And here we see that, look at what happens. The x's cancel out, and all I'm left with is h over h, which of course is just equal to 1. And as we saw, the limit of a constant, so 1 doesn't change as h approaches 0. And look at what we have. This function is just equal to 1 regardless of the value of x. All right? So what I want you to do is I want you to start doing these other ones. These we already know what the answer should be. But now, when we get to x squared, x cubed, we don't know what this function should be that gives us the rate of change for different x values. Okay, so what I'm going to say is let's pause the video. Let's actually stop the video and then give everyone about 15 minutes to work on this. And then in the next video, we'll start taking some of these up.